Okay, I'm going to teach you how to do electron configuration and orbital notation. One thing I'll mention, as you get to higher levels, you get more orbitals because as it grows, you're getting these empty spaces that are growing, and electrons repel each other, but as it grows, you get more room for electrons, and that's why the complexity of an atom increases as it grows. It's just that it gets more room for electrons as they get less repulsion. Okay, I'm going to keep this sheet handy. I'm going to keep my periodic table handy. Okay, electron configuration shows me the first and second quantum number. Orbital notation shows the third and fourth quantum number. If you have these together, they describe the domain of every electron, where the electron exists. Okay, so for any element, now I'll start with something simple. I'll start with sulfur, number 16. Okay. To do an electron configuration for sulfur, the first electrons always occupy the lowest energy level. That is called the off-ball principle. So we're going to follow three different rules for filling electrons. The first one is that electrons always fill the lowest available. So here's sulfur, but the lowest available is 1s1. So the first notation is 1, level 1, s-type orbital, and it fills 2. If I stopped right there, that's the configuration for helium, a noble gas. Well, once I fill helium, number 2, I have to fill, sulfur has, and this is one way to do it that's really good on the worksheet. Sulfur has 16 electrons. You have to show me where they all are, okay? And I'll show you something that's kind of cool about the other worksheet, how it's done. This is me just doing it off using, I always use a periodic table. So what comes after helium is lithium. Lithium's at level 2. I'm in this block, which is an s orbital. It fits 2. I now have told you where 4 of the electrons are, and I keep going. I come over here and I get to number 5, and it's still at level 2, but it's in a P. How many fit there? 1, 2, 3, 4, 5, 6. Okay. Now I'm at neon. I have a total of 10. I still haven't gotten a sulfur yet. I go to level 3. I'm in an S. 2 electrons fit in there. By the way, if I started at that 2p6 right there, that would be neon. If I stop right here, this would be magnesium. But I need to get all 16 electrons. I only have 12 at that point. I'm still in a 3, but I'm in a P. So I go 3, P, and then 1, 2, 3, 4. Okay? And that equals sulfur. Okay? And that's called an electron, the quantum numbers that you have right here. N equals 1, level 1, and L is an S, is a 0. If I go right here, energy level 3, L equals 0, an S. If I go right here, N equals 3, my L equals 1, a p orbital. So that's the secret to quantum numbers from that. Orbital notation. what they do is, I like to use circles. Some people use lines. Some people use X's, squares. I like circles because to me orbitals are kind of circular. So you're going to notate every orbital with circles. Well, if I have an S, you only get one circle. Here's another S, one circle. Your P gets 3. That's representing the 3 lobes of a P at the same energy level, all of them. This S would be another circle, and this P, even if you don't use them all, you have to show them all, even if there's just one in it. Okay? So now we get to more rules. Okay? So off-ball principle 1 is fill lowest available orbital. That means ground state. They are capable of jumping up, but that would be if you give them energy in the excited state. So if I started with my 16 electrons and I put my first one here, I'm violating off-ball principle. The first one has to be at the lowest energy. Secret, nobody knows that you did that. Only you know it. Okay? Now, the designations here are M sub L. M sub L is your orbital orientation. Meaning that if I have 3 P's, which I'm designating with 3 different circles, this is the 3rd quantum number. I just say orbital orientation. There's a nice fancy name for it, you know. It'll be magnetic quantum number. But it doesn't make any, you know, magnetism is related to the spin and direction of electrons, so it comes into play. But just as you know it, it's which orbital is it in. M sub L is plus or minus whatever your L is. So if I have a p orbital and my L equals 1, then my M sub L, it's a really fancy way for saying PZ, PY, and PX. I could call this one PZ, PY, PX. It gives them all a different designation. So plus or minus L with all whole integers in between, this would be +1, 0, -1. What that tells you? Tells you got 3 orbitals to choose from. That's your 3rd quantum number. Which one did you choose to go in? Okay? 4th quantum number is real easy. And this is where magnetism comes from. It's designated M sub S, and it's called spin quantum number. Well, electrons can spin this way, or they can spin that way. They can have opposite spins. So what you do is your spin can either be a +1/2 or a -1/2. Real easy. The spin is why I'm putting these half arrows on it, spinning up. Well, if one's spinning up, the other is spinning down. So I just put those 2 electrons in there. This one, up, down. Okay? Now we get to filling rules. If you're filling electrons with 3 different orbitals, the next electron to come in will not fill in the same one because they repel each other. It would fill this one, and then it would fill this one. This is called Hund's rule. So 1, 2, 3. So that's Hund's rule of multiple multiplicity. They fill one at a time, parallel spin. It could be down, 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 doesn't matter. Okay, but that's Hund's rule. You never have one going up and one going down, and you never have two in one orbital before you fill them all, at least one, if they're equal energy. Okay, and then we got to fill 6. Down, down, down. 3s2, 1 up, 1 down. Okay, and then 4. 1, 2, 3, 4. And that's what orbital notation looks like. Okay, what does it tell you? It tells you the m sub s, L, and this one would be a 0. If L equals 0, in other words, it's an S, then your m sub L equals 0. This is L equals 0, this is m sub L equals 0. This is L equals 1, plus 1, 0, minus 1. One thing you'll find, in an atom, no two electrons have the same set of 4 quantum numbers. There's something a little bit different about every electron in an atom. This is an L of 0, it's an S, this one was a P, so this one is designated 0. This is a P, L equals 1, so I got m sub L equaling plus 1, 0, minus 1. Okay, the spins. Well, the left-hand one is a plus 1/2. The right one hand is a negative 1/2. I don't care which one you call plus or minus. It doesn't matter. It's relative. So anytime here, plus 1/2, minus 1/2. And if you look at any of these electrons, they don't have the same energy level, the same orbital type, the same spin, and the same m sub L. Each one is a little bit different. Okay? So I'll write down the last 2 filling rules. Okay. Hund's rule of multiplicity. It says electrons fill multiple orbitals that word is degenerate. It means they're of equal energy. That would be like 5Ds. 1 electron at a time with parallel spins. And this is where magnetism comes from. If I was doing something like iron, you get 1, 2, 3. They fill parallel, and that's why iron ends up being magnetic. What would be wrong? Parallel, parallel. If suddenly you go opposite, that's violating Hund's rule. What's another violation look like? You start filling and you decide to put the next one there. Not allowed. So that's what Hund's rule would look like. Last one, Pauli exclusion principle. Sounds like something out of the mafia. Uncle Paulie. Okay, there was a scientist named Paulie, not mafia. No two electrons can have the same 4 quantum numbers. And before I get too long, I might mention that your nucleus also spins. They have figured out how to put people into giant magnets. It's called an MRI, magnetic resonance imaging. They can get a picture of your body by causing your protons to spin parallel. They'll put a magnetic field onto your protons and change their spin, and that's how an MRI works. It's all magnetism and studying your body. You can violate off-Paul's principle. That would be just an electron in the excited state is always a violation of the off-Paul principle. It can happen if it's excited. As far as I know, Pauli never happens. You only get 2 electrons in any orbital. So violations would look like this. You can't have them spinning parallel. Once they're parallel, that would give them the same 4 quantum numbers. And Pauli is why you can't have 3 electrons in an orbital. If you put a third one in there, not allowed. It's going to be spinning parallel. So that's why you can only have 2 electrons in the Pauli exclusion principle. Okay. There are some exceptions, and really, let me show you. I'm going to cut the video. I'm real quickly going to show you how to do the worksheet I posted. I like the worksheet because it really teaches you well.